Hello, and welcome to a digital lecture for Calculus 2 at Salt Lake Community College. In this video, we're going to go through section 12.4, the cross product. So we're going to talk about yet another way of representing multiplication with vectors, and specifically with three-dimensional vectors. The cross product is going to be purely a three-dimensional construct, something only true for a three-dimensional space. It does not have a relation for the first-dimensional space, or for one-dimensional space. The cross product, though, will be a little bit more complex than the dot product. And what also about the cross product is you will also result in a vector instead. Remember that the dot product resulted in a scalar, and the scalar product resulted in a vector because it was a scalar times a vector. Here we're going to multiply two vectors together and get a vector in return. Now what that vector is going to represent is a vector that is orthogonal to the plane created by your two initial vectors. So if you have a three-dimensional space like this, and you have a vector here and a vector here, then that is creating a plane of existence, a flat plane, and the orthogonal vector will be the vector that makes a 90-degree angle measure with that, so it comes out from it. That's what we will be creating with the cross product. Again, doing so is not so easy. In order to find the cross product, it's going to basically be like a matrix multiplication. You can either do it algebraically or with a matrix multiplication. Depends on which one you're more comfortable with. These ones I start with B and C instead of V and W, and you'll see why in a moment. If B is B1, B2, B3, and C is C1, C2, C3, then we're going to get the cross product, which we represent with a typical X for multiplication. You get the first component to be B2C3 minus B3C2, the second component to be B3C1 minus B1C3, and third component to be B1C2 minus B2C1. That's not the easiest thing to remember, because that's a little bit complex. If you want, instead, you can represent this as a matrix, and that's the reason why we have B and C to represent the last two rows, the second row and the third row. The first row, what we're going to do is put in I, J, K, which are the unit vectors of 1, 0, 0, 0, 1, 0, and 0, 0, 1. And that way we result in a vector, but already simplified into I, J, and K form. And to get this, we think about how you find the determinant of a 3x3 matrix, which is going to be this number multiplied by the determinant of these four, and then this number multiplied by the determinant of these four, and then this number multiplied by the determinant of these four. Notice that every time that we select a number, we're eliminating the row and column there and selecting the other four that are remaining. That's how we get I multiplied by the determinant of those four, and then J multiplied by the determinant of these four, but we subtract, that's one thing to keep in mind, and then K multiplied by the determinant of those four. That's how you find a determinant of a 3x3 matrix. Now, there are multiple ways of doing that. You can also do that with what is called the basket weaving method, if you're familiar with that. It's a nice way to do 3x3 matrices as well. If you don't like what I was talking about with the determinant above, what you can do for the basket weaving method is take the first two rows, or columns rather, and repeat them. So you have a 5x3. So you have IJ, K, IJ, and then you have the values for B and the values for C. Then what you're going to do to find out how to multiply I, you think about the diagonal going over to the right minus the diagonal to the left. So I, the diagonal to the right, would be B2C3, hence B2C3. And then the diagonal to the left, notice there's nothing left to that I, but the other I has a diagonal to the left made by B3C2. So that's how we get minus B3C2. Then you can get the same thing for J. J has to the right, it has J, B3C1, and then this J, B1C3. Notice how this one we don't need to worry about an initial minus because this already has it set up for us. If you compare it to the previous equation, this determinant of B1C3 would be first, but since that minus would actually rearrange it to put it second. So it does still agree with the previous evaluation. Then, lastly, with K, there's only one K, but we can make full diagonals. B1C2 minus B2C1. So that's how you do the basket weaving method. That can help a lot if you like to do with matrices instead. However, if you do happen to memorize the algebraic definition, that's fine as well. I personally like the algebraic definition as well. I like to think about it as, oh, this is the first component, then I'm not using B1 anywhere, and I'm doing B2C3, and then B3C2. So it flip-flops. I just need to remember what I start with. Then the second component is B3C1 minus B1C3. And the last component is B1C2 minus B2C1. I noticed that for the first and third one, it starts off with low and then high. So 1 or 2 and then 3 and then 1 and then 2 for the subscripts. Whereas the middle one is high then low. That's the flipped one. If I can remember that, I'm in good shape. Again, that's just how I remember it. I'm better with algebraic. I know a lot of people are better with matrices instead. Okay. Geometrically, you can define, I have here the orientation of the cross product vector by using what is called the right-hand rule. So what I was drawing earlier in terms of the three-dimensional construct of this with the vector coming out, in order to know, okay, is this vector going up that way, or is it going down this way, making a right angle with the plane like so. What you need to consider is, okay, what is the right hand rule? To do that, take your right hand, so take your right hand itself, and then point the fingers in the direction of your first vector. In B cross Z, you'd point it in the direction of B first. And then what you need to do is curl your fingers of your right hand towards the vector C. So whichever direction C is, that's the direction you should curl your fingers. You may need to spin your hand a bit. It depends. Once you have that done, then wherever your thumb is pointing is the direction of the vector. So, for example, if this was B cross C, then the vector I have would actually be correct, because I would point B, I'd point my hand and fingers up towards C, which is a little bit of an awkward angle, and I curl the fingers down towards C, and my thumb is going to be pointing down and to the right. If I had that flipped, though, if I had B here and C here, then I'd point my fingers down kind of towards my own body, and then I'd curl up towards C, and that would give me a vector going up this way because that's the direction my thumb would be pointing. So that's the right hand rule. I know a lot of physicists and people that work with electrodynamics probably are familiar with that. Also, if you consider the magnitude of the cross product, you actually get something a little bit odd. Remember that the cross product will result in a vector, so finding the magnitude is actually relevant. What you'll get to something that looks a lot like the geometric definition for the dot product of VW and cosine of alpha, or cosine of theta. In this case, you get VW sine of theta, and what you'll actually find is what is going to be the area for the parallelogram made by the two vectors. So if you had a vector here and a vector here, if you repeat these vectors, that creates a parallelogram. And the cross product magnitude will find the area inside that parallelogram. And then you have your vector coming out of that. So that's what the magnitude will give us. Okay. Now, what we need to do next is also think about what it means to be 0. Before, with the geometric definition of cosine, or of the dot product, we found that if the dot product was 0, that meant that they were perpendicular to each other. However, if you look at the magnitude calculation for the cross product, if the magnitude of is 0, what that means for non-zero vectors, so v and w not being 0, that means sine evaluated to be 0. So sine of theta would have resulted in 0. That only happens when theta itself is equal to 0, either degrees or radians. Which means that there is no angle in between them, which means that the two vectors are either on top of each other or they're parallel. So there is no cross. All right, let's do an example. We're going to find the cross product of v and w. Now I'm going to do it my way first, and then I'm going to also show it with the basket weaving method. If you do it with the algebraic definition of v cross w, where you're going to get for the first component, I think that might be enough room. For the first component, I'm going to not take the first component of the others. I'm going to take the second and third, and I'm going to go increasing. So I'm going to do 6, which is the second component, times the third component. So 6 times 2. And then I'm going to subtract away 0 times 3. Then, for the second component, I'm not going to take the second value for the vectors. I'm going to take the first and third, but this one we flip. So we start with the third one, 0 times -4, and then minus 1 times 2. Then, for the third vector, we eliminate, or the third component, we eliminate the third component originally, then take the first and second, and this one we go in logical order, so 1 times 3. So the first component of v times the second component of w, minus 6 times -4. That will result in 6 times 2, which is 12, minus 0. So 12. 0 times -4, okay, 0 minus 2. And then 1 times 3 minus 6 times -4, which is plus. So that's plus 24, and 3 is 27. And that should be it. Again, that's the algebraic definition. If you want to use this as vectors instead, or matrices, that's fine. To do so, we're going to consider this as I, j, and k, and we're going to put the first vector and then the second. So 1, 6, 0, and then -4, 3, and 2. To do basket weaving, I'm going to replace or repeat those first two columns, I and j, 1, 6, -4, and 3. And that's how I'm going to find my multiplications for I. I is going to give me my diagonal down and to the right. So 6 and 2. And then the diagonal over to the left, 0 and 3. And that's the first component, I. Notice that that already looks like what I did last time. And then plus, we're going to do that for j as well. J is going to be 0 and -4. And then 1 and 2. That's the second component. And then we have the last component, k. K is going to give me 1, 3. Minus 6, -4. For k. That gives us the exact same evaluations, 12i minus 2j plus 27k, or 12, negative 2, 27. I recommend giving a vector that's a result that looks like the vectors you started with. If I start off with ijk, I'd give my result as ijk. If I started off with the typical vector form, I keep that as well. So two different ways to find the cross product. Okay. Now, concerning the cross product, there are a few different properties for it that may differ from what you expect. The distributive property of a scalar with a cross multiplication works just fine. So if you have a scalar times v cross w, that's still going to give you CV cross CW. So that works just fine. But a lot of the other properties are a little different. If you do v cross w, that's not going to give you w cross v. That's going to give you negative w cross v. So if you flip those, you actually do result in a negative. And that's because if you think about the components, we would subtract the second one, so it does make sense that you get the opposite of one of the vectors when you flip them in a cross. Secondly, if you do a dot product, so u dot product with v cross w, which remember will result in a vector, that can also give you u cross v dot w, so that works rather nice. And if you do a triple cross product, u cross v cross w, that will actually give you the dot product of u and w, so the first and the third, multiply with v, and then the dot product of u and v subtracted and multiply with w. These last two are of particular note. Both of these are under the purview of what are called triple products. The first one is called a scalar triple product, and that's because when we have a dot product with something, we're going to get a scalar as an overall result. But this one is going to take a dot product with a vector minus a dot product with a vector, so it's really just a vector minus a vector, which is going to be a vector itself. So we call that a vector triple product, and that's all about to do with what you get as a result. All right. Now, the scalar triple product is useful because the absolute value of it, the absolute value of that scalar, will determine the volume of a parallelepiped. The parallelepiped is the three-dimensional parallelogram that you create. So if you have two vectors like this, then if you repeat that vector here and that vector here, and then if you consider the vector that comes out of that, this parallelepiped, or like a rectangular prism, but not always rectangular, could be slanted, that the absolute value of the scalar triple product will give you the volume of that. The vector triple product can be used to find the angle theta between vector u and the plane made by v and w. So we have v, we have w, this blue one that I wrote is u, and that is going to give us, if we consider the plane here, the theta angle measure here. That's what the vector triple product is going to be used for. And to find that, we keep in mind that the magnitude of v cross w is magnitude of v, magnitude of w sine theta. U cross v cross w, well, v cross w is itself a vector, so we could just do u for magnitude, and then the magnitude of v cross w, sine of theta. If you solve for theta, that'll give you the angle from u up to the plane. Okay. Well, the plane, not that, so that angle measure. Let's show how to do all of that. So, some more cross multiplication stuff. we're going to find the volume of the parallelepiped made by these three vectors. Then we're going to find the area of the face made by u and v. And then we're going to find the angle between u and the plane made by v and w. So we're going to find a few different things. First, for the volume. The volume is going to be the scalar triple product. The scalar triple product, as we see above, is represented two different ways. You can either do u dot v cross w or u cross v dot w. Either way works. It's really up to you how you want to do that. What you need to keep in mind with that is, okay, well, which one is easier for you? Which one do you think is the easier one to work with? I'm going to do the second. I'll just do u cross v and then dot w. If you want to do v cross w and then dot with u, that's fine. You can check me. I'm going to do 3, 2, and 1. Cross product, not dot product. Cross product with 1, 1, 2. And I'm going to dot that with 1, 3, 3. This cross product, if you want to do it with matrices, you can. I'm not. I'm going to just do this normally or algebraically. So 2 times 2 minus 1 times 1. And then for the second components, we have 1 times 1 minus 3 times 2. And then for the third component, we have 3 times 1 minus 2 times 1. Dot product with 1, 3, 3. So that gives us 4 minus 1 is 3. 1 minus 6 is negative 5. And then 3 minus 2 is 1. Three minus 2. Okay, just making sure. Dot product with 1, 3, 3. Dot product's a little bit easier. Just multiply the associated components. So you get 3 times 1 plus negative 5 times 3 plus 1 times 3. That gives us 6, and that gives us negative 15. So that will give us negative 9 overall. Take the absolute value of that, and we get 9 as our volume. All right. So that's our overall volume. Now we need to find the area of the face for u and v. This is actually why I did the cross product for u and v first, because I'm going to need that for the area of the face. To find the area of the face made by u and v, which is the face of that parallelepiped. So if we had 3 vectors like this, etc., up and up and up and up and up. Then if we're looking for one of these faces, maybe this bottom one, then to find the area of that parallelogram, we can find that by doing the magnitude of the cross product. So if we need to find the area of the face, we're going to do the magnitude of the cross product. So we're going to do the magnitude of u cross v, which we already found u cross v. We found that to be 3, negative 5, and 1. So we need the magnitude of 3, negative 5, and 1. It's going to give us 3 squared, negative 5 squared, and 1 squared. So 9 plus 1 is 10, plus 25 is 35. So we get root 35. And lastly, we need the angle between u and the plane made by v and w. That means if we're finding the plane made by v and w, we need to find that cross product. And to find the angle there, we're going to do the triple cross product. So the angle between u and v cross w, we're going to do the triple cross product. So to do so, we already have u. What we need to find is v cross w. So if I find v cross w, if you want, you could also just use dot products. But I need v cross w first. I think that's easier anyway. V cross w, where v is 112 and w is 133. Right? Yeah, okay, 133. If we cross product these, that will result in a new vector of 1 times 3 minus 2 times 3. So it'll be a negative. Then the second one will give me 2 times 1 minus 1 times 3. And then the third one will give me 1 times 3 minus 1 times 1. So that will give me 3 minus 6, that's negative 3. That'll give me 2 minus 3 is negative 1. And that'll give me 3 minus 1 is 2. Again, if you like to use matrices instead of cross products, it's fine. I'm just used to algebraic personally. So then, what we need to find, we need to have the magnitude of u cross v cross w equal to the magnitude of u, the magnitude of v cross w, sine of theta. So if we need to solve for theta, we need to find the magnitude of v cross w, which we now know. We need to find the magnitude of u, which is not hard, but we also need the magnitude of u cross v cross w. So we need to find this one. So u cross v cross w, where u is, if I scroll up, u is 321. Cross product with negative 3, negative 1, and 2. That will give me 2 times 2 minus 1 times negative 1. Then for the second component, we have 1 times 3, 1 times negative 3 rather, minus 3 times 2. And then we have for third, 3 times negative 1 minus 2 times negative 3. That gives us 4 plus 1 is 5. This will give us negative 3 minus 6 is negative 9. This will give us negative 3 plus 6, so that's 3. So now we should be able to use that equation. The magnitude of u cross v cross w, that's going to give us the square root of 5 squared plus negative 9 squared plus 3 squared. That'll be the magnitude of u cross v cross w, equal to the magnitude of u, where u is 321, so that's the square root of 3 squared plus 2 squared plus 1 squared. That's the magnitude of u. And then multiplied with the square root of v cross w, which is negative 3, negative 1, negative 2. So that's negative 3 squared plus negative 1 squared plus 2 squared. That's the magnitude of v cross w. And we have sine of theta. Solve for each of these. We have 25, 81, and 9. That should give us 115. Let's see, this 90 plus 25, yeah. So 115. And this one's going to be 9 plus 4 plus 1, so that's 14. This is also going to give us 9 and 1 and 4, so that's also 14. So that's just going to be 14 itself. Sine of theta. So we have root 115 over 14 equals sine of theta. Therefore, theta equals sine inverse of root 115 over 14. That, if we do that in our calculator, sine inverse of root 115 divided by 14, that will give us approximately 49.99 degrees, or almost 50. Or, in radians, about 0.873, I'll say, radians. So we have all three pieces. So we have the angle measure that was requested. That takes a little bit more time. We had the area of the face, and we have the volume. So we can do a lot with three-dimensional constructs just using the vectors that make it. With that said, I hope you have seen a few examples of cross products. I recommend trying it out on your own. But if you have any questions, feel free to put those in the comments below, or you can ask your instructor directly. I hope you have a nice day.